The fact that a class has all of the features of its ancestors plus just more stuff has a very important consequence, and that is that as far as the compiler is concerned, objects of a class are suitable substitutes for objects of their ancestor classes. So any place the compiler expects an object of type X, we can instead put any descendant of X. So for example, assume that hamster is a descendant of mammal. Well then, if we create a hamster object, we can assign it to not just a hamster reference as we do here, the reference H, but we can also assign the very same object to a reference of type mammal, to M. Because as far as the compiler is concerned, a hamster is a valid kind of mammal. The subtle part here is that Java doesn't presume to know what's actually going to happen to the reference mammal at runtime. Here it's very clear that we're assigning it a hamster object, but as far as the compiler is concerned, M is still a mammal, not a hamster. So if the hamster class has a method called runOnWheel, but mammal does not, it's okay to write h.runOnWheel because H is a hamster reference and therefore the compiler sees as okay, yes, the hamster type has such a method. But then even though the M reference is also holding the hamster object, we can't write m.runOnWheel because runOnWheel is not a valid method of the mammal class. Mammal class doesn't include it. As far as the compiler is concerned, M is just a mammal, and whether it's a more specific kind of mammal, it doesn't presume to know. And so to be consistent with static typing, it can only allow you to use the fields and methods which belong to the mammal class, not to any descendant class. One way to think of this is we can distinguish between the compile time type of an expression and the runtime type of the expression. The compile time type of M here in m.runOnWheel is always going to be mammal, but because there's always a potential at runtime that we might assign any kind of mammal to a mammal reference, the actual type, the runtime type, could be something else. It could be hamster. This use of subtypes in place of their ancestors works also in function calls, like say here, where we have a method called bar that returns void but expects a parameter of type mammal. Well then, we can pass it either a mammal object or we can pass it a hamster object because a hamster is a type of mammal. And similarly, if we have a method here, foo, which returns mammal, then we can return either a mammal or we can return a hamster. We can return anything which is considered a mammal, so that includes mammal itself or any subtype thereof. Recall from C casting, where we take a value and convert it into another type. And we did this with the type name we want to convert to in parentheses placed in front of the expression of the value. In the previous slides, we've actually been doing what Java considers to be a kind of cast. Specifically, it's what it calls upcasting. We're taking objects of one type and casting them up the chain of inheritance to some other type. So say, when we assign a hamster object to a mammal reference, we're actually casting it to mammal first. Now, whereas casting is usually thought of as a kind of conversion of a value, in this case, nothing's really happening to the object, nor is there really a new object being produced. It's just that for the sake of satisfying the compiler, we're telling it, yes, this hamster object is a valid kind of mammal. And with upcasting, actually, as we saw in the previous slides, you don't actually have to do it explicitly. If you'll just leave out the cast, Java will assume it's there. We can just leave upcasts implicit. In contrast, if we want to cast down the chain of inheritance, if we want to take, say, this mammal expression and tell the compiler that it's really a hamster, we have to make the cast explicit, otherwise the compiler will balk. The reason for this double standard is that when you do an upcast, the compiler knows for sure that a hamster is always a valid kind of mammal. What the compiler doesn't know here, though, is whether the expression M, a mammal reference, is actually at runtime going to hold a hamster. As far as the compiler can see, M here might at runtime be holding a proper mammal object, or it might be holding some other subtype of mammal which is not related to hamster. Because of branching, it's quite possible that the compiler, even if it put the effort to try and figure out what M at this point is going to hold, it might actually be indeterminate, because it might, say, rely on user interaction or something else from outside the program. So even in the cases where the compiler could figure out for sure that yes, this is going to be a hamster, it doesn't bother. And so the compiler doesn't presume to know whether at runtime this mammal reference is going to be holding a hamster or not. Instead, what happens when this downcast is reached is that the runtime performs a type check, and if the object in M is not a valid kind of hamster, then the language is going to throw an exception. So, whereas an upcast represents no kind of runtime action at all, it's purely just satisfying the compiler, a downcast is not just satisfying a compiler. We're not just telling the compiler that, hey, this mammal reference is okay to assign to a hamster reference. It also represents an actual type check at runtime. Because what we don't want at runtime is for our hamster reference to end up with something assigned to it which is not actually a hamster. So when we write this code, as programmers, we're telling the compiler, yes, we expect M to be a hamster, but we might have made a mistake because of branching. It might end up that M is going to be something other than a hamster. And that's why Java requires downcasts to be explicit, because they actually represent sort of dangerous operations. They're something we might screw up. And so it makes sense to effectively ask the programmer, are you sure you really want to do this? Finally, it's only possible to upcast or downcast objects. There's no such thing as, say, sidecasting, where you convert from one type to a totally unrelated type. Like, say, if you have a class duck and lamp, and presumably duck and lamp are totally unrelated, well then it's just not valid to cast a duck into a lamp. Under no circumstance is a duck a valid kind of lamp.